Welcome back to video 2 of chapter 12. So I said on this one to find the rate law, and you probably stared at it like, what? But if you read your notes, it said to determine the order, we need to plot these graphs. And if you have a fancy graphing calculator, you could have done that to see which one gave us a straight line. So if you plugged all that stuff in, which I know is kind of hard to do if you don't have a strong math background, it would have given you some information like this. And your graphs would have looked like this. Well, which one is our straight line? That bottom one. So, since 1 over NO2 gives us a straight line, the reaction is second order, which tells us our rate law. K times the concentration of NO2 to the second. Remember, K equals slope. So if you were to solve for K here, your slope would be 0.543 liters. And you could have used any concentration and rate to solve for that K. And this is pretty useful here. Maybe this is good to memorize the way things end up looking. Essentially a summary of everything we've talked about the last two here. So let's think about this graph. We have 4 graphs here. Which one illustrates a second order reaction? Well, what does a second order reaction do? What does our line look like? Well, it would have a positive slope. So what does that eliminate? A and C. And we know it would be 1 over A. So it has to be either B or D. How do I know which one? Well, D starts at 0, B doesn't. Can we have a reaction if we start with 0 concentration or no reactants? No. So it narrows us down to B being the correct answer here. Ignore the highlights here. Those are actually not the correct answers. No idea why they're highlighted. So if we have this reaction in its first order, which of the following would give us a linear plot? Okay, let's think about it. Have we even talked about log? Sure haven't. But we have talked about 1 over something, and we've talked about squaring things, which does look like first order. And we've talked about natural log, so I'm going to narrow it down to these 3 guys. And since it says it's first order, we know that something that's first order should look like D here, which would be the natural log of our concentration plotted against time. If you look back at your graphs, you'll see that. How about this one? What if it was second order? Which would yield this linear plot? What do we think would make it linear? Well, second order has to be what? 1 over something. So it had to be B. Alright, so we have another type of problem here. This one says we have a 0 order reaction, and it's starting with an initial concentration of reactant of 0.1 molar with this rate constant. What is our concentration after 1 second and after 100 seconds? Essentially, you're just going to plug it into the same equations here and be able to work that out. So I'm going to write this up, and I'll be right back. Okay, so what I did here was I looked at the fact that it was 0 order and referenced my proper equation, and I just plugged some information in. So I'm going to plug in my 1.65 times 10 to the negative 5th for my K. My time is going to change. 1 second, 100 seconds, and my initial concentration was right here. So for each one of those, I plugged in 1 second here, calculated, solved for T, got 0.999. Then I plugged in 100 seconds, and I got 0.998. My concentration did not change much in that 0 order reaction. Alright, pretty easy to plug those in. Now you guys try on this one. Pause it, give it a shot, come right back here. Okay, so here's what I did with this one. It only said for 10 grams of the liquid to evaporate. I just started with however much I felt like, and 100's a good number. So I pretended I initially had 100, and if 10 evaporated, that means my final was 90. Plugged in my numbers, solved for T. Got to get that critical thinking. Figure out what to do in these situations where it gives us something different in our question. Good. Alright, so to summarize, we only consider the following reaction. And there are two types of our rate laws: differential, which essentially means the curved line, and integrated, which is when we tried to figure out the slope by using a straight line. Once you find one, you can find the other, and our method of initial rates is used to determine that differential rate law. So for our integrated rate law, we find the concentration of these reactants at several different times, then find which straight line plot matches it, and that tells us what our differential rate law would be, or what the effects are of that guy. Now let's think about the way some reactions occur. Most chemical reactions occur in steps, like our reaction with our magnesium. It took 3 steps. We call these elementary steps. So rate law can be written a little bit more easily here, so we can use our coefficients for these guys. And we can call that molecularity, which means that is how many species I have that must collide effectively in order for my reaction to go forward. If it's unimolecular, it only uses 1 molecule, and we call that first order. If it's bimolecular, guess what? That's 2 of them, and we call it second order. And if it's termolecular, it means we have 3, third order. This is rare. Think of the chances of 3 things colliding at one time, and they're these little teeny molecules. Pretty difficult to do. So, like I talked about running the bases, our reaction is only as fast as our slowest runner, or our slowest step in our reaction. And that's what we call our rate determining step. That determines how quickly our reaction can move and what our overall order would be, or our overall molecularity of that reaction. So in order for something to be good, all those elementary steps must agree. That's why we've been balancing overall equations this whole time. And it has to also completely agree with that rate law that we determine experimentally. So here's an example. From the equations below that describe the 2 elementary steps of a process, write the rate law in the balanced chemical reaction. Well, these are just a show here. We're saying we have A and B going together to form C and D, and then we have C, and we're converting that to E and F. Well, what do you think we're going to have to do? We're going to have to only consider our reactants. But what are our reactants here? Are they A, B, and C? No, because C is technically a product here. So we can't consider it, and we also can only consider our slowest step, which is step 1. You'll always be told what your slowest step is. So we can write our rate law like this. Our A and our B are all that matter. Now we also have to think about each side of the equation and of course balance them out. Well, what's going to cancel here is our C. So our overall equation looks like this. C doesn't even matter. He's like a spectator, which we can call an intermediate. He doesn't matter. He's not a reactant or a product. Okay, so let's consider this reaction here, and it has this rate law. Well, what does the rate law tell us? It tells us that this is the slow step in our reaction, and it also includes some things here that tell us it could be 2 steps. So here's what our 2 steps look like, and we have some questions we can answer here. What is the slow step? Well, how do we know? Look at your rate law. H2ICl, there it is. That's our slow step. But what happens in between? Our HI is converted, okay? That guy's not in my final reaction. He's converted over here to ICl, and then, or he's combined with more ICl, and then he's converted to I2. So we can not only say, oh, this is definitely our slow step, because those are our reactants that are in our rate law, but we also know what our intermediate is. What would cancel here on both sides? My HI, so that's my intermediate. Okay, sorry, that might have been chunky. I had someone come into the room. And it tells me right here, there's my slow step. There's my intermediate. Okay, how about this reaction? Figure out your overall equation, determine the type of elementary reactions there are, and list all the intermediates. Then let's figure out the rate law. So if we're going to look here at our overall reaction equation, what do we have to do? We have to cancel species here that are similar on each side, so that guy goes away, and that guy goes away. Does everybody else stay? Well, one of these can cancel, but one of them stays. So our final equation is going to be like NO2 plus CO yields NO plus CO2. And then we need to ask what type of elementary reactions there are. Well, how many went in here? 1, 2. That makes it bimolecular. How many went in here? 1, 2. They went in bimolecular. So 2 bimolecular equations. And what are our intermediates? Well, we just canceled them. NO3 is definitely an intermediate that occurred in between my 2 reactions here. This doesn't count as an intermediate because it wasn't in the middle. It was at the beginning and the end. It just canceled. And if we want to know our rate law, what does that depend on? Well, it depends on my slow step. So my rate law is actually going to look like, so sorry, starting over here to go a little bit faster because I do not want to make another video for this chapter. So my rate law is going to be my slow step rate equals K times NO2 to the second, because there's 2 of them because it's bimolecular. So try this one, and your final answer here, pause it, your final answer is going to be my equation does match if I go back and cancel. What's my molecularity? Well, 1 went in unimolecular, 2 went in here bimolecular. What was my intermediate? MoCO5. Should be able to figure that one out. Do the same thing here. Pause it, try to figure it out, come back. My rate law is going to be my rate equals K times NO in my brackets here, and my BR2 in brackets here, and I'm going to take this and put it as a coefficient by my NO. Is it likely that this would happen? No, because it's termolecular. I'm putting 2 in here and 1 here. Remember, termolecular, really hard, probably 2 steps. How about this one? Try and break this guy down, and you can figure out the overall reaction here and write your rate law based on your slow step. Should be easy. You should know how to do that by now. When we think about collision, okay, stuff has to really collide with each other fast and hard and in the perfect way in order for a reaction to move forward. All these things affect it. When you think about activation energy, that's that energy we have to overcome, that hump we have to get over in order for a reaction to occur. Remember that this is our activation energy, this purple. That's the amount of energy I had to put in for it actually to occur. And our change in enthalpy here is the difference between our reactants and products, which tells us if it's endo or exothermic.
Analyze the changes that occur in energy and atomic arrangements as the reaction between nitric oxide and ozone occurs. Initially, the nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole. Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the molecules are in a transition state or activated complex, their potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state characteristic of the products.
Okay, so essentially what that was saying was, at the height here, this is the perfect place for them to bond. Once they pass it and go downhill there, the bonding's really easily, they'll all start to bond to each other, we'll form our new products. So they're in the perfect orientation here to break those bonds and reform bonds and come out looking like they should. Orientation is like, what if my water molecules aren't arranged right? What if they're not leaning the right direction? They have to be the right direction. They have to collide with enough energy in order for this to actually occur. We've already kind of talked about this a lot. What if we increase the temperature? Well, guess what? They're going to have more energy. They're going to collide. They're probably going to react better. This will increase our rate. Lastly, we have a catalyst. Remember, I hate that this says it speeds it up. It doesn't speed it up. What actually happens is it lowers the energy, but it doesn't get consumed. So this lower energy allows more stuff to collide, and it changes what our little graph looks like. So our catalyst makes our activation energy lower. But look, it didn't change our energy change. It's still the same. So it didn't really speed it up. Now here's what's happening with our catalyst. It's increasing our effective collisions. This many were effective here without a catalyst. It like more than doubled it over here. Catalysts are great. Homogeneous means same phase. And
reactant molecule.
Don't you worry, we don't have time for that. Heterogeneous means different phase. Hey, read through the rest of the notes, check the chapter if you have questions. Time's up.